Creationists will often invoke the mantra, evolution is only a theory. And they're absolutely right. Evolution by natural selection is a theory, but not in the way that creationists think that it is. Most of them are unintentionally equivocating the scientific definition of a theory with the colloquial definition. But before I get into what exactly a scientific theory is, I shall start with defining what a scientific fact, law, and hypothesis is. A scientific fact is very simple. It is an observation about the world that corresponds to reality. An observation is declared a scientific fact when it has been independently verified so many times that scientists can de facto treat it as a proposition that is always true. For example, a scientific fact would be, if a ball is dropped, then it will fall to the ground. Now, of course, strictly philosophically speaking, we can never be sure that an observation, no matter how many times it has been independently verified, will always correspond to reality. This is what is called David Hume's famous problem of induction. What happened in the past doesn't necessitate the same thing happening in the future. Even if it is the case that every time I've dropped a ball in the past, it has hit the ground, that does not mean that if I drop a ball again, the ball will fall to the ground. In other words, you cannot go from is statements like it is the case that every time anyone has dropped a ball, it has fallen to the ground, to a will be statement like, therefore, the next time a ball is dropped, it will fall to the ground. However, science must make this jump from is statements to will be statements because science could not be done without that first axiom. And for all intents and purposes, science operating and being predicated upon induction does work and has worked to describe and explain the natural world. Of course, science being successful in explaining the natural world while being predicated on induction does not mean that science will continue to be successful in explaining the natural world while being predicated on induction. In the formation of scientific laws, scientists will take these observed facts of nature and use them to create a law. A scientific law is solely a description of how some natural phenomenon behaves or works, and it is usually done through the use of math. But it is not an explanation as to why the natural phenomenon behaves in the way that it does. If I drop a ball, it is a fact that it will fall to the ground, and I can use the laws of gravity and the equations of kinematics to know how long it will take for the ball to reach the ground and how fast the ball will travel at a given moment along its descent. However, Newton's laws of gravity do not explain why gravity behaves in the way that it does as an inverse square law. Laws can often form out of scientific theories, but they can also precede them, just like Newton's laws of gravity and Kepler's laws of planetary motion preceded Einstein's theory of general relativity. A scientific hypothesis takes into account scientific facts and or laws and generates testable and falsifiable explanations for the scientific facts and or laws. But what does it mean for something to be testable and falsifiable? Well, if I drop my ball and see that it falls to the ground, I can come up with an infinite amount of ways to explain the ball falling to the ground, and disregard any information that goes against my explanation by simply adding to my explanation using ad hoc reasoning to explain away anything that doesn't previously fit with my explanation. This is known as the problem of underdetermination in the philosophy of science. I could posit that the ball dropped because the Earth and the ball both have immaterial minds, and the Earth telepathically commanded the ball to come down to it. This, however, is not a testable or falsifiable hypothesis, since there is no way to disprove the Earth did not command the ball to come down the moment I let go of the ball. The hypothesis must be something that is testable and falsifiable through experimentation or observation. Ad hoc reasoning still has its place in science as long as the new explanation added is added to an already established law or theory and is also testable and falsifiable. A real-world example of this was when scientists learned of the orbit of Mercury and that it did not correspond with Newtonian laws of gravitation. And so, using ad hoc reasoning, some scientists posited that there must be a planet Vulcan, a planet between Mercury and the Sun, which could explain the conflicting data. Of course, no such planet actually exists, but this same type of reasoning worked when scientists learned of the strange orbits of Neptune and hypothesized another planet, which was later confirmed in 1930 by the discovery of Pluto. In the case of these hypothesized planets, all one has to do to test this is to check to see if whether these planets are there or not. One could say that invisible giant gremlins floating in space are using long, invisible ropes to lasso Mercury and mess with its orbit. But this is an example of an unfalsifiable hypothesis to explain ad hocly the orbit of Mercury. Flat earthers, who are big proponents of ad hoc reasoning, are not being scientific when they use ad hoc reasoning, since, despite the ad hoc hypothesis being testable and falsifiable, they are only adding to an unestablished and, in fact, scientifically defunct flat earth model. Using ad hoc reasoning in the way that flat earthers do makes their hypothesis pseudoscientific. It is important to note that predictions do not count as proof for a scientific theory. Proofs are only found in deductive forms of knowledge such as math and logic. As science relies on induction, the furthest a theory can get to being true is being the most reasonable thing to believe given the current evidence. We cannot know anything with absolute certainty in science. Now that we know that we need to generate testable and falsifiable hypotheses to explain natural phenomena in science, we must go about testing these hypotheses, and the way science does that is to use these hypotheses to make predictions. The scientist will take into account these facts and/or laws and generates a testable and falsifiable hypothesis to explain the data. And then, the scientist must use the hypothesis to make concise, novel, testable, and falsifiable predictions. If a hypothesis is true, then the hypothesis can be used to predict something that we do not know yet, which can be confirmed via experimentation or observation. Once this experimentation and/or observation are done by several other scientists who do their best to falsify the hypothesis, and the methodology and findings are confirmed through peer review, and other scientists can use the same hypothesis to make other novel testable predictions that are later confirmed, the hypothesis has now been promoted to a scientific theory, which means that it is a coherent group of propositions formulated to explain a group of facts or phenomena in the natural world and repeatedly confirmed through experimentation or observation. So the key difference between a law and a theory is that laws describe a natural phenomenon, and a theory explains why a natural phenomenon works in the way that it does. Einstein's theory of general relativity was an explanation for why gravity behaves in the way that it does, as an inverse square law. Einstein posited that gravity was the literal bending of space and time in proportion to the mass of an object. Einstein's theory of general relativity accounted for the strange orbit of Mercury, but of course, this is not enough evidence for his, at the time, hypothesis to become a theory. What Einstein needed were concise, novel, testable, and falsifiable predictions. He used his hypothesis and the mathematics behind it to predict that light from a distant star would follow the warp of space and time created by the mass of the sun, and this was later confirmed. General relativity has also predicted gravitational waves, gravitational lensing, gravitational time dilation, and an expanding universe and black holes, all of which have been confirmed through either experimentation or observation. General relativity is now a well-established theory. Evolution by natural selection is, like general relativity, a scientific theory. It has been independently corroborated by predictions in several different fields of study and by several different scientists. There are an overwhelming amount of confirmed predictions, but here are a few. The prediction of finding transitional fossils between dinosaurs and birds being confirmed by the discovery of Archaeopteryx. The prediction that there must be dead or unexpressed genes for making vitamin C being present somewhere in the human genome, since humans descended from animals with the ability to make their own vitamin C, was confirmed. The genetic relatedness of the great apes with humans was confirmed. Predictions about observable speciation in the lab and in the wild was confirmed. Bacteria evolving to become more resistant to toxins was confirmed, and the list goes on and on. I have linked a website in the description listing many of the other predictions of evolution that have now been confirmed. Evolution by natural selection, like general relativity, has earned the status of scientific theory. It is a theory, and that's pretty much as high of an honor an explanation can get in science. And so that's all for today. If you enjoyed the video, please give it a like and subscribe for more content. Thanks.